Hello everyone. In this short video, I'm going to talk about naive Bayesian classification. So there are two things that are important, and I'm going to make a separate video about the theory of this, but one is the Bayesian, which is based on the Bayes' theorem, and then the naive assumption. So here we need to generate data, and for generating data here, I use this method called mate classification, and I bring it under a Scikit-Learn data set. And then I also bring train test split from model selection under Scikit-Learn to split my data. So the naive Bayesian classification is based on the maximum a posteriori or map estimate of the data, where it uses the Bayes theorem and says that the probability of y, where y here is the class of data and x are the training features, the inputs, right? It says that if you have one feature, then p of y given x equals what? Based on the Bayes theorem, right? If we use the Bayes theorem, it is basically p of joint of x and y divided by p x, right? And p of joint x and y can be written as what? P of x given y times p of y, and then the whole thing divided by p of x, right? So this is the Bayes theorem if you have one x, or if you have a vector x which has more than one feature, then you can use it basically as a bunch of x's, right? So it has individual x features, so it can be a vector. And then since this px is constant and does not have anything to do with classes, we only focus on the numerator. And so in order to get the class here, we say it is the argmax of this function, which is the argmax of the numerator, right? So we say y hat, the estimation of the class, is argmax of what? This numerator term. As we said, the denominator is constant, has nothing to do with the class. Now, this p of y, right, which is the probability of the classes, we call it the prior information or prior function, or prior probabilities. And then this one, probability of features coming from specific classes, we call it the likelihood function. So if we calculate this numerator term and make sure we find the y that makes this guy the maximum, that y is going to be our class. Now, how do we calculate this term here? When you have several x's, like x1 all the way to xn, so we calculated by the naive assumption that all of these x's that you have in the vector x, all of these x1, x2, all of them are independent from each other. So probability of xi given xj is the same as probability of xi, okay? Or the probability joint of xi and xj equals what? Probability of xi times probability of what? Xj. These are the same way to say these two, xi and xj, are what? These features are independent. The other thing you say is that they are identically distributed, okay? So they come from the same distribution. So if the features are independent and identically distributed, we call them IID, right? I comes from independence, and then identically distributed is ID. So we say our features are IID. That's the naive assumption, because many times in reality, the features we use for training, they are not independent from each other, okay? And many times they could be. Some of them could be identically distributed, but not necessarily all of them, okay? So this is the theory part of it, and again, my goal is not to go over that necessarily here. The other thing I want is I need the numpy here and Then, in order to perform the Gaussian naive Bayesian classifier from Scikit-Learn under naive Bayes, I bring in the Gaussian NB. Now, the other thing I have here is, remember I said these xi's, xj's, they are identically distributed, but they come from what kind of distribution? Here, we assume that they are coming from a Gaussian distribution. They are continuous variables. In my case, in this example, they are not categorical variables. They are continuous variables coming from a Gaussian distribution. All of these individual likelihood terms. And so for that reason, I bring in the Gaussian NB, the Gaussian naive Bayesian, right, to do my classification. So what do I do here? First, I generate my data. Here, I'm not going to read the data. I'm going to generate data. How do I generate data? Well, one of the things you can do is you can either directly type them, or there is this new function that I wanted to introduce to you, make classification, which can generate for you a lot of random numbers, and in general form for me an n-class classification problem. So it's not just a binary. You can have as many classes as you want. In my case, it's just 2 classes, right? But you can make it an n-class classification problem. And you pass to it the number of data that you want, the number of features each data has, and then if you have prior probability for the data. So here, I assume that the class 1 happens 20% of the time, class 2 happens 80% of the time. So you give that as weights. So these weights are the initial prior probabilities that you give to the function, okay? These are the estimates of py initially. And the important thing is this make classification, generate this random data, and the cluster of the data that they are generating are what? Are normally distributed. Okay, so the assumption that we made that these are, in this case, Gaussian, that is correct. This guy will generate data from a Gaussian distribution. So it gives me the training data and the labels, and then I split it into training data and testing data using train test split. I use 40% of the data for test, 60% for training. I don't want any random shuffling. Then I create my object for the naive Bayesian classifier using Gaussian NB. Then I pass to it the x and y of the train and ask it to fit. So here it is going to find the models of the Gaussian that basically they need. It's going to create the model. And then once it has the model, it is going to get me the y hat. Now I can pass to it my test data and ask it to predict the values of the y. And for x data, I have the y's, so I can check where the predictions in ypred are different from y-test. Right? The cases that ypred is against y-test, they are different. Those are the misclassifications. So here, you see in my print, I say, show me the classes that y-test is not equal to what? Y-pred. So this gives me a vector, right? Gives me a logical vector, and I use dot sum method from NumPy and add all the ones together, and that is sum of all cases that are not classified correctly. Out of how many data points? Out of exactly what? X dot underscore test dot shape 0. Remember here, I'm only applying it to X test data, which is how much? Which is 40% of the 200, right? So it should be 50 data points, 50 test points. Out of 50 test points, let's say so many of them are not classified correctly. It shows me that. And the other thing it can show me is now that it has these predictions and everything, it can update my initial weights of the 2 classes. So I can get it from this GNB dot class underscore prior underscore. And this gives me updates with those weights, okay? Based on the data that I have done and classification. So let's go ahead and run this. There we go. So it says out of 80 points, I have 3 misclassifications. Let's make sure. Yeah, actually it's 80. I don't know why I said 50. It's 80 points because it's 0.4 times 200, right? So I have 80 data in the test, and only 3 of them are not classified correctly. So my accuracy is what? Basically 1 minus 3 over 80, right? So 3 over 80, so it's going to be 3.75. Minus that is 96.25%, which is relatively high. And then the updated weights of the classes are now what? 0.175 and 0.825, which are close to the initial ones, but a little bit, of course, altered after the classification is done. Okay, so this is how you create a naive Bayesian classifier. You feed the data, you can predict any new thing, you can get the new updates of the class weights or priors, and here is how you create some random data. Hopefully this video was useful to you. I'll see you in the next lecture. Thank you.